All right, so we're going to talk in this chapter initially about the Pythagorean theorem, okay? Um, Named obviously after this Greek man named Pythagoras, okay? There is documentation that this theorem was being used long before Pythagoras is accredited with it. There's also discussion that it wasn't necessarily him that should be credited with it, but one of his followers. So, kind of give you a little bit of history about just mathematics and thinking and philosophy and all that kind of stuff, and how that all kind of worked in social structures back then. Like right now, like I don't want to say we, but society, because not everybody does this, okay? But a lot of people like idolize and follow like great athletes or great artists, that kind of thing, right? Okay, would you guys say LeBron James probably has a pretty big following? Would you say, I don't know, people like Lady Gaga, they have big followings, right? And people idolize them. They have cronies, okay? So those are the people that are like high elite status in our society, right? Thousands of years ago, okay, when people like Pythagoras or Socrates or Aristotle, Plato, those types of people were alive, okay? It wasn't whether you could, how high you could jump and dunk a basketball or how good you could sing a song. It was how intelligent you were, okay? How did you think? How well of a thinker you were, okay? And philosophers, okay, mathematicians, scientists, those were the people that were the elite class of society, and those were the people that had followings. That kind of make sense? Okay? So Pythagoras, he had his own group of essentially cronies, okay, that kind of worked underneath him. Plato was the same way. Socrates the same way. Okay, Aristotle same way. So there's discussion that Pythagoras actually gets credit for this theorem, even though it was being used, the concept was being used long before him. But the credit should actually have been to somebody that was working under him, okay, or for him, or something like that. But regardless, we call it the Pythagorean theorem. It's usually a picture you see with the Pythagorean theorem here, dealing with areas. Okay, we'll talk about why that's the picture eventually. Come down here and give you the verbal description that you'll see in some textbooks. It says, in a right triangle, the square of the hypotenuse is equal to the sum of the square of both legs. We have actually done this. We've actually done this a lot so far this year. You guys remember the distance formula? Distance equals the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. Okay? Well, let's work our way backwards from that. If I give you the distance formula as distance equals x2 minus x1 squared plus y2 minus y1 squared, okay? If this point right there and that point right there are in the coordinate plane and they're x1, y1, x2, y2, that distance b is found by subtracting the x coordinates of those 2 points. So that might be b instead of, right, it's just a redefinition or redefining of those terms. Okay, this here, okay, if that point right there and that point right there where x's and y's in the coordinate plane, then y2 minus y1 would give me that distance a. Okay, and that's underneath the square root, and that would give me then d, which is going to be this distance here, which you see that they're relabeling that as c. And now how do I get to the Pythagorean theorem? Well, if I square both sides, I get c squared is equal to a squared plus b squared. Does that make sense? Okay, and we kind of talked about that early on in the beginning of the year, when I first introduced the distance formula to you, but the distance formula and the Pythagorean theorem are one and the same. Every segment that you draw in the coordinate plane, unless it's vertical or horizontal, is a hypotenuse of some right triangle with legs of x2 minus x1 and y2 minus y1. So that's how we see the theorem verbalized in words. Obviously, then here is the picture, or the algebra. A squared plus b squared equals c squared. I'm going to generally write it c squared equals a squared plus b squared, because you'll see a reason why later on. But the symmetric property allows you to write it as a squared plus b squared equals c squared if you want to. The one thing that you need to pay attention to is that they're always going to give you two parts. They're always going to give you two parts. You have to realize that those two parts, what are they? Are they both legs? Because that's what goes on the a squared plus b squared side. Those are legs. Okay. C is the hypotenuse. So it might or eventually be more beneficial to you to write your formula that way. Leg squared plus leg squared equals hypotenuse squared. Because in the past, I would I'd give you situations where, 4 or 5 problems in a row, I give you both legs. And you go leg squared plus leg squared equals hypotenuse squared, and you solve for C that way. And then the 5th question or 6th question, I give you a leg and a hypotenuse, and nobody differentiates that I gave you a leg and a hypotenuse, and they take those two values, they square them, add them together, like they were both legs. Does that make sense? So you got to be careful. You got to pay attention to what are the components that they are giving you, because they fit in a specific spot in your formula. Okay? A squared plus b squared equals c squared. I would argue that this is probably the formula, or at least the geometry, that you have the most experience with from previous classes. You talk about this in other classes? 7th grade, 8th grade? Okay. Anybody know why that is true? I'm going to give you one, at least today, one proof of why this is true. Okay, so I'll give you a minute to draw that blue and yellow figure. Basically, all I've done here is I've taken a right triangle. I've taken this triangle right here, this darker blue one on the bottom left, and I just keep kind of rotating it, cutting and pasting it all the way around, and creating this perfect blue outlined square. Okay, with those distances of A and B. We're going to go through an algebraic proof of this. This is only, obviously, one proof, and like I said, I might, depending on the time we have, we might do a couple more different style proofs for this. A quick Google search will inform you that there are at least 367 validated proofs that are different for the Pythagorean theorem. Okay, this is just one of them. And this one, I think this one is maybe appropriate because it deals with area. And area generally is a little bit easier of a concept for us to think about. Basically, what we're going to do here is that we are going to find the area of this overall square two different ways. And if I find the overall area of that square two different ways, what should be the result of those two different ways? Should I get the same areas or should I get different areas? I should get the same areas, right? Okay, it's the same shape. So regardless of the route I go, I should get the same area. So one of those ways, okay, let's just look at this as if it was all a blue square. Just looking at the overall blue square. Okay, if it's a square, and I know it's a square because I told you, going off of chapter 6, we got a right angle there, Told you that's got to be a right angle, and that's got to be a right angle, right? So we got 4 right angles. This length is A plus B. That length is A plus B. That length is A plus B. And that one's A plus B, correct? So we have created a square here. Let's go ahead and find the area using our formula for the area of a square. That length, A plus B. Would you guys agree with that? That length, A plus B, correct? Okay. How do I find the area of a square? If I had this square right here, and this was S, and that was S, how would I find the area of that whole thing? S times S, right? Okay. It's essentially a special case of length times width for a rectangle. Okay. Well, if right now, if my sides are A plus B, then the area would be A plus B times A plus B. Would you guys agree with that? Okay. So if I multiply this all out, doesn't that mean that I have A squared, so I'm going to FOIL this, A times A is A squared, B times A, and then A times B. I'm just going to write this as A times B plus B times A, and then B times B, last times last, would give me B squared, right? Are these two terms in the middle of the same thing? Is AB the same thing as BA? Okay, so I'm going to rewrite this as area is equal to A squared plus 2AB plus B squared. Now, based then off of that information, we should have A squared plus 2AB plus B squared. When I know what A and B are, I know exactly the area then of that square. But there's different ways of doing this. There's a different way of finding the area. Can I chunk this up into 5 smaller shapes? Do you guys agree that I could call this shape 1, shape 2, shape 3, and shape 4? Guys agree with that? And then this here would be shape 5. Is that doable? Okay. Now, what is the relationship that you guys know about shapes 1, 2, and 3? How do they relate to one another? Okay, they'll have C in common, but what else do they have in common? A and B, right? And they also have right angle in common, correct? Okay. So these right triangles are all congruent. Whatever technique you want to use, side, 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 angle, side, angle, side, angle. Those 4 triangles are congruent. So let's do this. The area formula for a triangle is 1/2 the base times the height, correct? Okay. So let's just look at triangle number 4 down here. Okay. What would you consider the base to be? Would it be B, A, or C? I'm going to say it's B. Okay. It could be C. It could be A. It doesn't matter. It's not C. Okay. If you remember, we talked about altitudes being the height. Okay. Back in chapter 4, I think it was. An altitude is the H for a triangle. Find the area. And the base is then the segment that altitude is drawn to, okay? Well, this segment A right here is an altitude. It goes from a vertex perpendicular to the opposite side. So if A is H, then the opposite side it goes to, B, would be the base. Does that make sense? Now you could do the same thing and say that this is the altitude, that B is the altitude, and A is the base. But it still gives me this, 1/2 AB. Is that okay? But that's just for this triangle number 4. You've got triangle number 3, which is the same thing, right? So I can do this one of 2 ways. I can either say, okay, well, I'm going to take 1/2 AB, that's this triangle here, plus 1/2 AB, which would be this triangle, plus 1/2 AB is this one, plus 1/2 AB that one, right? We have 4 of them total. So what I'm going to do is rewrite this as area of, I'm just going to say all triangles, just so I can keep track of what these areas are, is 4 times 1/2 ABs. What does that turn into, though, if I take 4 times 1/2 AB? 2 ABs, right? Does that make sense to everybody? Okay. So that's adding up those 4 triangles. And that's true no matter what A's length is, no matter what B's length is. Those 4 triangles, area is going to add up to 2 ABs. Okay, so if I'm trying to find the entire area of this overall square, I still have not, when I add those 4 triangles up, I still have not dealt with the yellow area yet, right? Well, that yellow area is a square with sides of length C, right? So isn't the area of that yellow C squared? So then the area of the yellow plus the area of the blue would be C squared plus 2AB. If I add those 2 things together, it should get that thing there, right there, right? Does that make sense? Okay, so over on the left-hand side, when we looked at the overall square's area by finding it that way, and on the right-hand side, we found the overall square's area finding it that way. What do we know about these 2 A's? They're the same, right? It's the same square that I found the area for. So if those A's are the same, what's that tell you about these 2 things? Shouldn't A squared plus 2AB plus B squared equal C squared plus 2AB? What amount is on both sides? 2AB. Get rid of it. Does it leave you with A squared plus B squared equals C squared? Okay. So a lot of times just writing this stuff here, a lot of times with proofs, actually that's the wrong symbol. They might write like a little square here and color it in. I forget who its name is. The guy's name started with an H. It's called, whatever his name is, Tombstone. Basically what it means is we're final. That's our last step. We've proven what we were set out to prove. The QED at the end of a proof is Latin for the phrase, we have proven what we set out to prove. Something like that. Okay. But if you ever see that as you progress through other courses, that's just a way of formally kind of finalizing or wrapping up a proof to tell everybody that you're done. Does that make sense, though? Okay, now that's just one. Like I said, there's like 370 almost proofs that generate this conclusion. Okay. All right, so here we've got our first example, and that's going to lead us to a vocabulary word. Okay. So right here, I've got a right triangle. I've got legs of 3 and 4. So if I go A squared plus B squared equals C squared, A is 3, B is 4. Trying to figure out what C squared is. That's 9 plus 16 equals C squared. 25 equals C squared. So what's C going to be? You have to take square root now, right? Okay, and this is why in the last chapter we attempted to learn as much as we could about radicals, because they're going to be pretty much in every single problem we see in this chapter. Here we're going to put square. Now, when I introduce a square root, there's a plus or minus, but what is this C representing? It's a distance, correct? So that's why we usually neglect the minus and we just say that we have C equals 5. Okay? Now, when you get, this is pretty rare, when we get distances for a right triangle that are all integers, okay, like 3, 4, and 5, we consider that group a Pythagorean triple. Okay? 3, 4, 5 is a Pythagorean triple. All right? Something that contractors will do, people that do construction. Let's say that I'm on a job site and I've got, whatever it may be. Maybe they're 2 2x4s. Maybe I'm a mason and I'm laying brick or whatever. But let's say I want to make sure that I'm looking down on this structure. So this is, whatever it is, I want to see if it's a right angle. Okay? Maybe I'm coming over to this wall, this corner right here. Okay? And I want to check to see if this corner is a right angle. What I'm going to do is I'm going to measure out from a spot. I'm going to mark a spot in the corner. I'm going to measure out this direction 3 feet. Okay? Then I'm going to measure out on this wall a direction, in that direction, of 4 feet. Does that make sense? Okay? So I'll demonstrate that here. So we've put a mark on the corner here. We'll measure out 3 feet there. We'll measure out 4 feet there. So I'm checking to see if this is a right angle. Okay? If that is a right angle, what should that distance right there measure to be? If it's a right angle, it should be 5. Okay? So that's what a contractor, someone working construction will do. They want to see if this is a right angle, measure out 3 feet, measure out 4 feet, take tape measure from those 2 spots, and see if it gives me exactly 5 feet. If it does, right angle. If it's smaller than 5 feet, then that means the angle is closer or tighter than 90 degrees. Does that make sense? So it would be less than 90. If it's longer than 5 feet, then that tells me that that angle is obtuse. Okay? Does that kind of make sense? All right. A lot of times that's called that profession is a 3, 4, 5 check. Okay, so they're gonna check to see if they've got lengths of 3, 4, and 5 to guarantee that they got a right angle. Here's a list of some common Pythagorean triples. We just see them over and over and over again, that they become kind of second nature. 3, 4, and 5, 5, 12, 13, 8, 15, 17, 7, 24, 25. As you get, we'll see them replicated over and over in our assignments in this course, but they really start to show themselves in a trig course, just because of all the different types of problems we do there. Those are convenient values to start problems with. Obviously, to check to see if your integers are a Pythagorean triple, the largest value has to be the what? It has to be the hypotenuse. Okay? So in the 3, 4, 5, the 5 would be the hypotenuse. In the 5, 12, 13, the 13 would have to be the hypotenuse. Okay? So if I gave you a triangle like this, and I said that's 4 and that's 5, can this be 3? No. Okay? So you just got to keep that in mind. Just because it's still 3, 4, and 5 segments, the 5 over here is identified as the hypotenuse. Any multiples of these are also Pythagorean triples. So a lot of times they might write this instead of 3, 4, and 5. They might say like 3n, 4n, 5n. They might say 5n, 12n, 13n. And then they'll say, well, n is an element of like your natural numbers. So that means n could be 1, 2, 3, 4, and so forth. Okay? So if n was 1, that would give you 3, 4, 5. If n was 2, it'd give you 6, 8, 10. If n was 3, it'd give you 9, 12, 15. Does that make sense? So each one of those groups would also be a Pythagorean triple. And that's what this bullet down here is saying in a more simplistic way. We talked about this. For solving for a distance, we introduce a square root. There is a plus or minus, but we usually disregard the minus because it's referring to a distance. All right. So a lot of times, like I said early on, they're going to give you just very simplistic, like these are 7th grade, 8th grade math questions. Okay. If I want to find C, I'm going to take a squared plus b squared equals c squared. A is 9. B is 14. Doesn't matter which one's which. Because I've gone 14 squared plus 9 squared. What property allows me to do that? Commutative. Okay. So 9 squared is what? 81. Anybody know what 14 squared is? 196. Good. Okay. So I'm going to add those together. So I get c squared is equal to, is that 277? Okay. All right, so 277, pretty large number, right? Anybody know anything special about 277? What would be a number, if you're going to try, what would be a number maybe you try to divide 277 by? Maybe try to divide by 11. Okay, what about, anybody try 7? Okay. Let's say I didn't know, but 277 is prime. Okay. If I didn't know this, maybe I could start dividing it by perfect squares to see if it does reduce any. And the perfect squares that I need to try would be the ones that are less than half of 277. So I would try numbers like what, 1, I don't know what, like one less than perfect square is less than 135, 136, something like that. But no, that's going to get you up to what's the largest one there? 1 be 10. Okay, so 100. What I'm trying to get at here is that radical 277 is not going to divide by anything. It's prime, and therefore, if it's prime, it's fully simplified, right? We're going to, and I sent this out on the last e-learning day. There's going to be questions that involve us having to simplify radicals, and we're going to get to the point where, like every single one we come across, we're not going to go through the like day 1 algebra of how to do that. Okay, so I sent you some links to reference, to refine your skills, relearn your skills, or even just learn them the first time. But you have to utilize those. Okay. This one here, this is something that we're going to come across as well. The values that they give us here are not whole numbers. So generally, when they give us values like this, they will not ask you to write an answer with a radical in it. Does that make sense? If it's a decimal that is not 0.0 showing up as one of the components, they will then usually ask you in your answer, go ahead and round it to whatever decimal place. Okay, and this is you guys talk about sig figs in chemistry, right? This could be an application. We won't do it, but this could be an application where it says, okay, we've got however many sig figs in this problem, then that's how we're going to produce our answer or write our answer using the same amount of sig, or the largest amount of sig figs. Does that make sense? We're not going to do that, but generally speaking, like I said, if it's a decimal component, A or B or C is decimal, then usually the answer they're going to want is decimal as well. So we'll just say C squared is equal to 4.5 squared plus 6.3 squared. Now, because I know it's going to be a decimal answer, I'm going to have to grab my calculator, right? Okay. So when I do this, Like, I'm just going to leave it that way. Does that make sense? I don't find it beneficial for me to take that number, write it down, take 6.3 squared, write it down, and then take the sum of those and square root. I'm just going to let my calculator do all the work for me. So we'll go square root 6.3 squared plus 4.5 squared. That's what we get. Okay. That makes sense? Okay. I don't think it's very efficient to say, okay, 6.3 squared is that number, 4.5 squared is that number, and then take, okay, 39.69 plus 20.25, and then square root 59.94. Gives me the same result, but I just think it's a little bit more efficient to let the calculator do all the work. Is that okay with everybody? So this is where people get hung up. They run into problems with this. This is intended. I don't know if it's intended, but it's one of the sections out of Chapter 8 that should not be a huge issue to us. Okay, or Chapter 8. But we miss a lot of problems with it because we get ingrained in the type of problem that they present us with initially, where they give us a leg, and we got to find the hypotenuse, like the last 2 or 3 that we've done. Now they give me a leg, so I'll take 7 and square it. They use x for the other leg, and then 14 for the hypotenuse, right? So in this case, I've got to set things up this way, okay? I always, every year, I get a handful of students that no matter what 2 values they give you, they always square those and add them together. That's not the approach that you take. Remember, it's leg plus leg, both those being squared, is equal to the hypotenuse squared. So now I get 49 plus x squared equals, we already did this, so it was what, 196? So then x squared, okay. What's 196 minus 50? 146. So if I subtracted 1 too many, I want to add that 1 back in, and that should give me 147, right? Okay. I look at that, I'm going to take square root. And right away, I start thinking, when I'm taking square root, I'm trying to find divisors of 147. And I think right away, this is just my train of thought. I try to do long division right away, and I see 14 and I see 7 in that 14 or 147 number. Does that make sense? What is that? What goes into 14? 7. What goes into 7? 7. How many times does 7 go into 14? 2. And how many times does it go into 7? 1. So 147 breaks down to 7 and 21. Does that make sense? Okay, just doing that long division in my head real quick. What's 21 break down to? 7 and 3. Okay. So then I get that as a pair of 7s that can come out in front. So that basically tells me that 49 was the biggest perfect square that will divide 147. And when I take 147, I divide it by that perfect square of 49, it yields a 3 as the other factor. So 7 radical 3 will be the answer that they ask for in regards to x. Is that okay? The rest of this explains what we call the converse of the Pythagorean theorem. So if the Pythagorean theorem is holding, if it's true, the triangle you have is a right triangle, right? The converse would be if, again, let me phrase it this way. What we've been doing, we have a right triangle, so the Pythagorean theorem is true. The converse says, if the Pythagorean theorem is true, then you have a right triangle, correct? So they might ask you to go through and say, can you check, does this triangle right here, does 85, 84, and 13, is that a right triangle? Okay, we don't know yet, but if it was, what segment would be the hypotenuse? The 85 would be the hypotenuse, right? So can we say 85 squared equals, now we're going to ask, we don't know this yet, we're asking this question, does 85 squared equal 84 squared plus 13 squared, right? And all we've got to do, if these numbers, obviously these numbers, we probably don't have them committed to memory what those perfect squares are. So I'm just going to say 85 squared is that number right there. Does that give me 13 squared plus 84 squared? Does that make sense? Okay. That's essentially doing that 3, 4, 5 check, but doing it with distances of 13, 84, and 85. Okay. So because that all checks out, these two numbers right here are the same. So that means this relationship was the same, meaning that the Pythagorean theorem does hold. So the only time the Pythagorean theorem holds is when you have a right triangle. So yes, indeed, this thing is a right triangle. If they were different, it would not be a right triangle. So let's come down here to this scenario here. And this is why I like to use c squared equals a squared plus b squared instead of a squared plus b squared equals c squared. I like the c squared to come first because I can do this. I'm going to put this third statement in here, okay? And that's the one we started with. If c squared equals a squared plus b squared, then you have a right triangle, right? Okay? But if I get a relationship that says c squared is less than a squared plus b squared, then that means that the triangle has to be an acute triangle. Okay? I like this because if I think about acute and I think of right and obtuse, obviously we know right is what we're looking for with the Pythagorean theorem, so that's the equality statement. But if I think about acute and obtuse and I compare them based on their definition, acute, definition-wise, means less than, right? So does it make sense why I like to write c squared first? Because that then brings in the inequality that is less than. Okay? So if I get c squared is less than a squared plus b squared, that's an acute triangle. If I get c squared is greater than a squared plus b squared, that means it's going to be an obtuse triangle. It just means that that angle has to open up more than 90 degrees to touch endpoint to endpoint with your segments A and B. Okay, for that segment C to touch endpoints with A and B. Where if, based on what we know about inequalities, if I wrote it as a squared plus b squared, that right there says the exact same thing that right there does. But when I read this, it's greater than, right? A squared plus b squared is greater than c squared. And then people get stuck in their mind, well, greater than must be obtuse. But that would not be the case in this situation. It'd be acute. Does that make sense? That's the reasoning why I think it makes sense for us to put C first in our argument. Okay. They might give you, 3 or 4 segments, not 3 or 4, 3 segments that they ask you to identify the type of triangle, whether it's right, acute, or obtuse. So if I give you, let's say, 9, 13, and now I'm going to give you a third segment here. What do these two numbers have to do in order to compare to this third segment? Doesn't this sum have to be greater than that third segment? You guys remember that? Okay. So I'm going to make this third segment 20. So I know those 3 segments will make a triangle. I want to know, is it right, is it obtuse, or is it acute? Okay. Well, what would C be here? What would your hypotenuse, if this is a right triangle, what would C be? It'd be 20. So I'm going to say, does 20, is it less than, is it equal to, or is it greater than, so 20 squared, is it one of those compared to 13 squared plus 9 squared? What's 20 squared? 400. What's 13 squared? 169. What's 9 squared? 81. Okay? Now, this 400 is greater, it's greater than 169 plus 81, right? So, because this is c squared is greater than a squared plus b squared, that means these three create an obtuse triangle because of that relationship about c squared compared to the sum of a squared and b squared being greater than. Does that make sense? Okay, if it said less than, we would be acute. Does anybody have questions over Pythagorean theorem? There's some examples here that we may go over in the next day or so, just depending on your performance on 8.1 in Math Excel. We might come back and do these. I think you guys are going to be okay. In the past, 8.1 has never been a real issue. Like I said, the only concern I have is make sure that you know what parts they're giving you. Are they giving you two legs, or are they giving you a leg and a hypotenuse? Okay.